Hello, my name is Burak Kantarci. I'm an associate professor at the University of Ottawa and the founding director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa. I'll be presenting our paper titled Machine Learning Driven Event Characterization under Scarce Vehicular Sensing Data. And this paper appears in the proceedings of the IEEE International Workshop on Computer-Aided Modeling and the Design of Communication Links and Networks 2020. And this work is in collaboration with Raven Connected. So let me start with the problem that we are tackling here. The problem that we're working on in this paper is driving event characterization. So this is mainly used in accident prevention systems or some driver scoring systems. And what is aimed here is detecting anomaly in the driving patterns and or identifying predefined risky behaviors of the drivers. And these decisions are mainly based on either visual data or sensor data. And the sensor data is acquired either from the in-vehicle sensors or the sensors that are in personal devices like wearables or smartphones. In the literature, there are threshold-based systems that are being used to detect these sort of behavior. And there are also some systems that leverage some intelligence. I won't go through them here in this short talk, but we provide a nice overview of these works in our paper. So if you're interested, I encourage you to go through our paper and that particular section. I will elaborate on this data scarcity problem that we've been encountering in this study. So the data set that we're working is pretty imbalanced because there's shortage of anomaly in the driving data. And even less critical driving behavior does not exist significantly or visibly in this data set. And vast majority of the data consists of normal driving behavior. So in order to cope with this, we had to come up with a solution, which I will talk about in a few seconds. Now, this is how we gather the data. So Raven sensors are being used to get 4 different types of aggressive driving behavior patterns or risky driving behavior patterns and normal driving behavior. So these risky driving behavior patterns are harsh braking, aggressive acceleration, harsh left turn, and harsh right turn. And there's also a normal driving behavior pattern. Now, what are we doing to cope with the scarcity of these events in our data set? Okay, so we pursue a 2-step training procedure. In the first step, the training signals are duplicated and added random noise, and these signals go through an encoder network, and once their vector representations are obtained, they go through a decoder, which outputs multifold and synthetic data at the end. So for the test procedure, we don't need duplication or random noise addition here. So the test data directly goes into the encoder, and then the vector representations are obtained, and the classifier classifies this data under the corresponding category. And at the end, we use also dimensionality reduction to represent the data in 2 dimensions and to visualize it on the device for the user. So we need 4 steps, briefly, for generating this synthetic data. First is duplicating the input signal into n individual signals, which is 10 in our case, and adding random noise to each individual duplicated signal. And then these noisy signals are fed into an encoder, and they are encoded to a lower dimension. And then finally, these vector representations are decoded to obtain the synthetic signals. So at the end, we have synthetic signals representing the behavior of the original event. So we are using a recurrent autoencoder in the training process where the event classification network is also using here a softmax function with cross-entropy loss function. Our experimental settings are presented here, as you can see. So the recording frequency here is set at 25 Hertz, and we split the data set 70% by 30% for training and testing respectively. As a baseline solution to compare our proposed method, we use a special type of recurrent network, which is convolutional long short-term memory. So that's going to be our baseline. And I'll be presenting you now the numerical results here. As you can see, the autoencoder-based solution increases the accuracy and precision by 12% compared to the baseline. And the recall and F1 score metrics can also be improved by 11%. And not only that, we also significantly reduce the false predictions, as you can see here, compared to the baseline. And here, you can also see the 2D mapping of the original input data and the 2D projection of the vectorized data, which is our synthetic data that we generated from the original signal. As you can see here, the driving patterns, the clusters regarding these driving patterns become more visible and become bolder. So to conclude, the encoded vector representation here that we propose offers a more accurate input for the detection systems. And the synthetic data that we generated here also improves the training procedure, the robustness of the training procedure. And of course, we can cope with the data scarcity problem by using the autoencoder-based approach here. And we create more variety in the data set by following this procedure. And at the end, we can also significantly reduce the false predictions, as you saw in the previous slides. So this concludes the talk. Thank you very much. I hope you enjoyed it. If you would like to read more about the details of this work, I encourage you to read our paper. Thank you.